square roots captured in the wild. So, this is our foundational figure for constructing most basic shapes in Euclidean geometry and in the geometry that comes before Euclid. Call it ancient geometry or sacred geometry. I don't necessarily intend to try to get into any sacred aspects, although I suppose we could touch on them here a little bit. So your basic shape is the circle. It has a center point, which doesn't necessarily show up, although it shows up by default in this program as sort of a little circle, a sort of polka dot. It's got a color, it even has an outline. But a point is supposed to be infinitesimally small. It's supposed to be indivisible, having no length or breadth or size at all. It's a location without extension. Extension is what you have when you have two locations, but no, a point is just one. Anyway, no need to belabor that. So the other part of the circle is the large curved line, which is its circumference, and its circumference can be thought of as an endless continuum of points, which are all equally distant from the center. So you take a circle, and then you create another circle, let's say construct another circle of exactly the same size by simply leaving the compass setting unchanged. Or, if instead of using a compass, perhaps you're simply using a string, perhaps the compass collapses when it's not drawing a circle. Well, in that case, you just place your center point anywhere on the circumference of the other circle and extend that string to the center, and then draw a circle using that as your radius. So these two circles share a common radius. Both of them have the same radius determining their size, and one of them sits on the circumference of the other. Each sits on the circumference of the opposite circle. And they overlap, and their overlap intersects their large curved lines at 2 points, and those are the intersections. And if we connect those 2 points with a line, well, we have a vertical line. And if we connect the other 2 points with a line, well, we then have a horizontal line. And that gives us an angle of 90 degrees, or what you'd call a right angle, let's simply say. Another feature of the angles of these large lines, and let's just sort of de-emphasize the circles for a minute. Well, the angles of our lines are all equal. The amount of distance, let's say. Let's see here. Let me do one more thing. Let me draw another circle. And this will be the unit that we'll use then to determine the distance between the lines. Well, I assert that the distance of this line then is equal to the distance of this line, which is equal to the distance of this line, which is equal to the distance of this line. Which is to say that all of these lines are equally inclined to one another. None of them are more open than the other. Now, if you start twisting the lines just a little bit away from this pattern, some of them will be greater and others of them will be lesser. This is something that you find as a basic problem, or a basic sort of qualitative measurement in Euclidean geometry, that some angles, simply speaking, are greater than others. You don't even have to get into degrees, hours, minutes, seconds, radians, none of that. You just notice that some of them are bigger than others. And if you have a common reference, like that third circle that I drew in the middle, then you can determine which angles are greater and which angles are lesser. Anyway, let's go ahead and go back a little bit. And that, by the way, made a square. That's okay. We'll just go ahead and go back to this point. And we have some other things at this point that I'd like to mention. So we did a square in one way. There's another way we could do a square. I'll draw another circle from this bottom intersection point of the two circles to one of their centers, one or the other of the center. It's equally distant, that intersection point, from either of the other two centers. And this one is as well, and this one is, well, it's equally distant to the intersection point that forms the center of the third circle. Anyway, so now look at what we've done with this. We've now got two more lens shapes. We've got two more circles that intersect and upon which vertical lines can then be drawn. Now those two vertical lines that I just added are now equally distant. That is to say that they're both one radius apart, just as the first two circles are. Okay. So I'm going to lighten these lines just like I lightened the lines of the original circle, and we'll go ahead and we'll lighten some of these other lines as well. Alright, now the vertical lines also intersect our first two circles here and here, and below here and here. And we can note that there is a 90-degree angle there. There's a 90-degree angle there, and if we drew them from the other side, whoops. Let's see, there's a, yeah, let's recenter that a little bit. Alright, so then from the other side, so that's another 90-degree angle, and then there will be another 90-degree angle. And those arcs that I drew from those top two intersection points, they're arcs with the same radius as the original circles. So we have four 90-degree angles and four angles and four points which are as that is to say the bottom 2 points, the ones that are blue here, are just as far from each other as they are from the points above them. And those 2 points above are just as far apart. And the lines that comprise the sides and the top and the bottom of this figure are all parallel. And that is a square. Deductively, apodictically, indubitably, a square. Now, a square, this square happens to be 1 unit in width. It's 1 unit in width and 1 unit in height. And since the radius of our first 2 circles is our natural basic unit, this is our natural unit square. It is 1 square unit. And if we are measuring area, we will measure by this. So the square root of our unit 1 is 1. Okay? So the base of the square, or the length, or the top, is our unit 1, our square root of 1 as well. Now, you can find the diagonal of this square, and the diagonal of this square is in fact the square root of 2, because you can build a square which has this length as its base, which is twice the area of this square. So the square of area 2 its area is 2, and the root of the square is the diagonal of the other square, so that means that that is the square root of 2. The square root of 3 is from the top and the bottom of the oval. This is our vesica piscis, our mandorla, our fish splatter, our lens shape. And its height is the square root of 3, and its width is 1. And if you draw a rectangle with those dimensions, that is your root 3 rectangle. Your root 3 rectangle can enclose the vesica piscis, the mandorla, the almond or seed-shaped. You can call it a pointed oval. The word oval has a connection with ova, which means the egg. It is a pointed egg. It is a football. It is a lens. It is a mandorla. Vesica piscis. Anyway, that is also the form that gives rise to all of our other basic geometric forms, and therefore might be conceived of as giving birth to them. So we've got our square root of 1, the base of our square, the square root of 2, the diagonal of our square, the square root of 3, the height of our vesica piscis, the square root of 4. The square root of 4 is 2, and 2 appears here in any number of ways. Each circle has a diameter of 2. Since it has a radius of 1, it has a diameter of 2. We drew one square. We could draw another square. We could construct another square just below it. And the height of that pair of squares is 2. Okay. So that is our square root of 4, the vertical there. Okay, what about our square root of 5? Well, the diagonal of our root 4 rectangle is in fact the square root of 5. So that's the square root of 5. I don't believe we have the square root of 6 or the square root of 7 here in any straightforward way, or the square root of 8. But we do have the square root of 9, which after the square root of 4, the square root of 9 is our next whole number square root. So the entire width from here to here this red line, that is to say, is our square root of 9, because that is the length 3. But we're missing the square root of 6, of 7, and of 8, which are all irrational number square roots. But notice something about these square roots. Each one of them is a definite length. We tend to think of square roots as numbers that just go on and on and on and on, these long decimal things. But they don't go on forever. It's just that it takes forever to precisely approximate them. But to construct them, to describe them geometrically, they're a number, and they lie between the other numbers. The square root of 9 is not bigger than 4. The square root of 9 is not bigger than 3.5. In fact, the square root of 9 is not even bigger than 3.1. The square root of 5 fits right in here neatly, and it's smaller than the square root of 9, and it's bigger than the square root of 2. The square root of 2 lies between 1 and, well, heck, it even lies between 1 and 2. It lies between 1 and the square root of 3. It is a definite length which terminates, and which can be drawn fairly precisely, about as precisely as you can draw any length. And if you're using the square root, like let's take a basic use case. You use the Pythagorean theorem because you want to know if the building foundation that was constructed by the masons, ahead of you and, the rest of your carpentry crew coming along to put the walls up, the floor joists and the walls, well, you want to know that that building foundation was laid out square. You're going to use the Pythagorean theorem to test it. So you're going to measure one length, you're going to measure another length, you're going to square those two quantities, add them, and then you're going to take the square root of the sum, and then you're going to lay your tape measure diagonally across the two places that you measured, and you're going to see if that foundation measures on the tape measure what you came up with in terms of the square root of your sum. Okay? And if it lines up, you've got to find a mark on the tape measure. You're not going to find, 1.61819238725. No, you've got to look at a specific place on the tape measure, and you're going to know that the next tick on the tape measure, the next millimeter or 12th of an inch or whatever, is going to be too big. Okay, you're going to have a point on the tape measure where you say, if my measurement falls here, it's too small. You're going to have someplace else on the tape measure, you're going to say, if my measurement falls here, it is too big. And your number is going to be pinned down as well as you possibly can, because you're dealing with an irrational quality. It doesn't line up neatly with the markings on your tape measure. It doesn't line up neatly, as a fraction. But you can find out about where it is, and you're going to have a fairly precise idea of where that square root is. Anyway, I'll go ahead and stop there for now, because, what else is there to say about this? So, all right, well, over and out.